Hi friends, good morning. I welcome you all for today's session. Right, in today's session we'll be studying with Euler's formula for buckling of a column with one end fixed and other end pinned or hinged. Right, so this is case number 3. Already we have studied two cases. Right, so let me begin with the today's video lecture. So first I need to consider a column such that its one end is fixed and the other end is pinned. Right, so let me consider that. So if I consider this as the column, let us say this end is fixed, so I'll just give the fixed support. Right, I'll place a rigid plate over here and the other end it is pinned. Right, now let us say the total length is L. As usual, the total length here is L, so I'll just extend this so that it is convenient for me to mark the lengths. Okay, so this the total length here is L. Right, now let me mark the deflected part or the final shape of the column after buckling. So since here it is fixed, it will be something like this up to certain distance. Right, so this will be the final shape. Here the slope will be 0 and at this particular point the value of y will be equal to 0. Right, so since it is fixed, so it should go parallel to this beam, sorry, parallel to this column up to certain extent, and then from there it will get deviated. Right, now as usual there is some load, compressive load, which is acting, which is causing the buckling. So that compressive load I'll show it here. Let us say this is the compressive load and its value is P. Right, now the reaction here, which is equal and opposite, will be P. Since you are having this one as the fixed support, right, so whenever there are fixed supports, so you know that there are three reactions which will be popping up. So this will be the reaction, vertical reaction. We'll also be having a horizontal reaction R, a horizontal reaction R, right? Then you will be also having a moment, right? So what will be the direction of the movement? Let me decide that direction. Okay, so before I could mark the direction of the movement here, what I'll do, I'll just consider some section XX. So I'll just mark the section over here. Right, so this is X. So this distance here is taken as X, and this distance is the deflection, it is taken as Y. Now at the section XX, if you just check out, this particular P is causing a moment which is in the anti-clockwise direction. P with respect to section XX, it is causing an anti-clockwise movement whose magnitude is equal to P into Y. Right, so it is in anti-clockwise direction. To avoid that, at this fixed end the reaction should be in clockwise direction. So the reaction will be like this. Reaction will be like this, right? So P is the action, this P is the reaction. Now here, since it is a fixed support, right, so you will be also be having a reaction like this. So in order to counter this reaction, so that this point, the hinged point, will not move from its position, so there should be one more reaction here in this direction. Now what happens, these two reactions, I'll also call it as this reaction as R, this R and this R will counter each other, they cancel each other, both will be equal and opposite. P and P will be both will be equal and opposite. So P with respect to the section Y, sorry, with respect to the section X at a distance Y, it will cause P into Y, so it will create a moment. So that moment is anti-clockwise, so that moment is resisted by this clockwise moment at the fixed end. So once if these things are clear, then things are pretty simple. It is just about substitution, applying the boundary condition and getting the result. Right? So we know that deflection is equal to moment caused. We know that deflection is equal to moment caused at the section xx. Right? So what is deflection? I told you need to remember this ei d square y by dx square. So what is the moment caused? So moment caused here, let us say at this particular point from this section xx, right? So यहाँ से जो भी reactions आ रहे हैं, it may be p or it may be r. So what moment it is causing with respect to this section xx? So it is p into y. So p into y, it is anti-clockwise. That is the reason it is taken as negative, right? Then r into x, right? So r into x, so r is coming like this. So which is this direction? R into x. ये कौन सा direction है? Just look at the sense what I am making here, how my finger is being rotated this direction. So this direction is once again anti-clockwise. So once again it is minus r into x, right? So in bracket, if you want, you can write here it is anti-clockwise, so it is taken as negative, right? Now further, e into I d square y by dx square can be written as y double dash is equal to minus p into y minus r into x, right? So now as usual I'll put let beta square is equal to p divided by ei, right? So if I want to put this, then I'll be dividing this entire equation by ei. So y double dash is equal to minus p divided by ei into y minus r into x divided by e into I. Right? So if you just proceed further, therefore y double dash is equal to minus p divided by ei is beta square. So it is minus beta square into y. So it is minus rx divided by ei. So if you want to put it in the form of a differential equation, it is y double dash plus beta square y is equal to minus rx divided by ei. Right? So this is the differential equation whose solution I need to get in order to get the minimum compressible load which causes the buckling. Right? So the solution to this differential equation is given by the solution to this equation is given by, right? So once again this solution you need to remember here, it is y is equal to a sine beta x plus b cos beta x minus r into x divided by p, right? So I'll just mark it with a green ink, which means that you need to remember this or it is important. Right, now I'll be applying the boundary conditions. So let me take this as equation number 1. Right, so what is boundary condition 1? BC is boundary condition 1. So from the diagram what you can see here is at x is equal to 0, y is equal to 0. If you take this as the origin, at x is equal to 0, y is also equal to 0. If you take this as point L, at x is equal to L, y is 0. Right? So at x is equal to 0, y is equal to 0. At x is equal to L, y is equal to 0. That was the second condition. And the third condition is at x is equal to 0, y dash is also equal to 0. The slope here is also equal to 0. So there are three equations or boundary conditions which you need to use. First I'll be using at x is equal to 0, y is equal to 0. Right? So the first one, at x is equal to 0, y is equal to 0. So what equation 1 becomes? If you put it in this equation, so let me check out. X is equal to 0, y will be 0 by default. So it is a sine 0 plus b cos 0, cos x into 0 minus 0. Right, so what is the value of sine 0? Sine 0 is by default 0. Right, cos 0 is 1, so therefore b is equal to 0. Right, so you got the value of b as 0. Now if you put the value of b as 0, therefore equation 1 becomes, so it will become y is equal to a sine beta x minus rx divided by p. Q, because if you put the value of b as 0, that entire terms become 0. Now I will use the second boundary condition, boundary condition number 2. So boundary condition number 2 is at x is equal to L, y is equal to 0. So in this equation, y is 0, a sine beta into L minus r into L divided by p. Right? So therefore, a sine beta L is equal to, a sine beta L is equal to r into L divided by p. This you take it as equation number 2. Right? Now moving further, let me use a third boundary condition. So the third boundary condition is boundary condition 3. I already told you at x is equal to L, y dash becomes 0. So if you put it in that equation, then what I'll be getting here is, I need to first find out y dash. So let me find out y dash. So y dash is equal to a sin x, derivative is cos x, so it is cos beta x into beta minus r divided by p, because differentiation of x is 1. Right, now in this, if you put y dash is equal to 0, a cos beta into L into beta minus r divided by p. So therefore what I'll be getting here is a into beta into cos beta L is equal to r divided by p. So this you take it as equation number 3. So dividing equation 2 by equation 3, we get, right, so equation 2 is a sine beta L, a sine beta L divided by a cos beta L is equal to RL by P, and here it is R by P. Right, so if you just resolve this, a and a gets cancelled, a and a gets cancelled. Right, so what I'll be getting here is, here it is beta into a cos beta L. So sin beta divided by cos beta is tan beta L divided by beta is equal to RL divided by P into P divided by R. So once again common terms gets cancelled. So therefore tan beta L is equal to beta into L. Right? So when tan theta is equal to theta, and this is the condition, tan theta is equal to theta, beta will be nearly equal to 4.5 radian. Right, so squaring on both the sides, squaring on both sides, so it is beta square L square, so 4.5 square is 20.25. Right, so we know that, but beta square is equal to P divided by E into I. So I put the value of beta square. So it is P divided by E into I into L square is equal to 20.25. Right? So I put the value of beta square. So if I put that, I'll be getting this value. So therefore, P is equal to 20.25 into E into I divided by L square. Right? So slightly I'll modify this. So therefore, P is equal to 2.052 pi square E into I divided by L square, and that is equal to P crippling or P critical. Right? So if you just multiply this pi square, that is 22 by 7 the whole square, into this, you'll be getting 20.25. So let me show you that value. So pi square into 2.052. Right? So you can just check out, it is 20.25. So that is what I have got here. Right? So this is the formula which gives me the minimum compressive load or minimum critical load required for buckling in a case where one end is fixed and other end is free. Right? So that's it for today's session. Have a great day. Bye bye.